Somewhere north of San Francisco, there's a crack in the earth that almost nobody has ever heard of. It does not have a famous name like the San Andreas Fault. It has never been in a movie. But in the last 5 weeks, this quiet little crack has done something it has never done before in its entire recorded history. It has broken twice, and the second time, in the last days of July, it did not just send out one earthquake. It sent out a swarm of more than 160 small shakes, all in the same tiny patch of ground, all within a few hours. Earthquake scientists have a special phrase for what might be happening here. They call it a potential main shock. That phrase sounds calm and official, but it is actually one of the more unsettling things a scientist can say. It means the earthquake that just happened might not be the big one. It might just be a knock on the door before something bigger walks in. Here's the strange part. Nothing about this earthquake was supposed to be scary on paper. It barely rattled a few dishes. Nobody got hurt. If you searched the news the day it happened, you probably would not have found a single headline about it. And yet, tucked away in the fine print of an official government report, one small sentence quietly admitted that the earthquake everyone just felt might only be the beginning. By the end of this video, you will understand exactly why that matters. You will find out why this forgotten little crack runs in a straight line toward one of the most crowded places in the entire country. You will hear about an almost identical warning sign that fooled scientists in Japan 10 years ago, right before their worst earthquake in decades. And you will learn about a strange, silent patch of ocean floor on the other side of the planet that either means everything is fine or means the exact opposite. This story starts small in a town most people could not find on a map. It does not stay small for long. 1. 2 shakes 5 weeks apart. Let's start with the town itself. Cloverdale sits at the top of California wine country, tucked between hills and vineyards, about 2 hours north of San Francisco. If you have never lived there, you have probably never said its name out loud. It is the kind of place you drive through on your way to somewhere else. Quick thing before we keep going. If this story makes you want to actually be ready for something like this, we put together a simple earthquake survival guide ebook that walks you through exactly what to do before, during, and after a big one hits. It is linked in the description and pinned in the comments below. Now back to the video again. Almost everyone who grows up in California learns about the San Andreas Fault in school. It is the big, famous crack that runs almost the entire length of the state, and it shows up in every earthquake movie ever made. What almost nobody gets taught is that the San Andreas is not the only crack out there, and it is not even the only dangerous one. Underneath the hills and vineyards to its east, there's a whole family of quieter faults that most people will live their entire lives without ever hearing named. One of them happens to run right underneath Cloverdale. But underneath Cloverdale, and running for miles in both directions, there is a crack in the solid rock of the earth. Scientists call this kind of crack a fault. Think of it like an old scar, a spot where the ground has broken before and can break again. Most of the time, a fault just sits there, quiet and still. The two sides of the crack are squeezed together so hard by the weight of the planet that they do not move, at least not smoothly. On June 24th, everything changed. Just after 8 in the morning, the ground near a stretch of forest close to Cloverdale let go. The shaking measured 5.6 on the scale scientists use to size up earthquakes. If you are picturing a movie-style disaster, that number might not sound huge, but 5.6 is strong enough to knock dishes off shelves, crack plaster walls, and genuinely frighten anyone standing nearby. The machines that measure ground movement recorded some of the roughest shaking ever picked up in that part of Northern California. Thousands of homes lost power. A few people were hurt. And here is the part that matters most. It was, as far as anyone has ever recorded, the single biggest earthquake this particular fault has ever produced. Not the biggest in 10 years. The biggest ever. Think about how strange that is for a moment. Scientists have been recording earthquakes with real instruments in California for well over 100 years. In all that time, watching the same fault every single day, they had never once seen it produce anything this strong. Then, on one ordinary Wednesday morning, it did. That is not the kind of thing that happens by accident. It is usually a sign that pressure has been building for a very long time, quietly, out of sight, until it finally found a way out. On its own, that would already be a big story. But 5 weeks later, in the last days of July, the same stretch of earth broke again. This time the shaking measured 4.3, a bit smaller and a little closer to Cloverdale itself. A 4.3 earthquake by itself is nothing special. Small earthquakes like that happen somewhere on Earth almost every single day. Most of them get one line on the local news and are forgotten by lunchtime. Except this one came with a warning label attached. When scientists looked closely at what happened after the shaking stopped, they noticed something strange. It was not just one earthquake. It was followed, within a few hours, by more than 160 additional small shakes, almost all clustered in the same tiny patch of ground. That is not normal. A typical earthquake that size might stir up a dozen small aftershocks before everything calms down again. A dozen is boring. A dozen is expected. 160 is not boring at all. It means something underneath that patch of rock is still actively rearranging itself, the way a stack of plates keeps wobbling and resettling long after someone bumps the table, except this stack is made of solid stone, miles underground, and it just got bumped hard. That is exactly why scientists reached for the phrase potential main shock instead of simply calling it a regular earthquake. It is their way of admitting something a little uncomfortable. There is no machine on Earth, no sensor, no computer program that can tell you the moment an earthquake happens, whether it was the big one or just an opening act. That answer only becomes clear afterward, once you already know what came next. So here is where things stand after these two events. A fault that almost nobody outside of science could name has broken twice in 5 weeks. The first time was the strongest earthquake it has ever produced. The second time came wrapped in the kind of aftershock swarm that makes scientists sit up a little straighter at their desks. Nobody has been seriously hurt. No buildings have fallen down. But something underneath Northern California woke up in June, and it has not fully gone back to sleep. People felt the shaking far beyond where it actually happened, too. Scientists actually keep a website where ordinary people can log on after an earthquake and describe exactly what they felt, whether it was a gentle wobble or a hard jolt that knocked something off a shelf. Hundreds of people filled out one of those reports after the July earthquake, from small towns close to the epicenter all the way out to cities more than 60 miles away, including San Francisco itself. Almost everyone described the same thing: dishes rattled. Picture frames went crooked on the wall. A few people said their whole house creaked for a couple of seconds. Nobody reported a cracked sidewalk. Nobody's house came down. On the official warning scale, this earthquake got the lowest possible level. The same green light you would see for a completely harmless event. On the surface, in other words, this looks like almost nothing happened. But here's the thing about earthquakes that most people never think about. What happens on the surface and what is actually happening deep underground are two completely different stories. The surface tells you how something felt. The pattern of aftershocks tells you what is really going on down in the rock. And this pattern is the kind that makes the people who study this for a living choose their next words very, very carefully. It helps to remember that California has been here before in a much bigger way. In 1906, an earthquake tore through San Francisco and flattened huge parts of the city. In 1989, another major earthquake, remembered by the name Loma Prieta, shook the Bay Area during a World Series baseball game and collapsed a section of highway. Both of those earthquakes are proof that this part of the country is fully capable of producing the kind of event that changes a region forever. Neither of those famous earthquakes happened on the little fault running under Cloverdale. But as you are about to find out, that quiet fault is a lot more connected to the rest of the region's earthquake story than its size or its fame would ever suggest. Before we go any further, if you're the kind of person who likes knowing what is happening under your own feet before it ever becomes a headline, this is a good moment to hit subscribe. We are tracking this exact fault day by day right now, because the scientists' own forecast says the next several days are the real test. If anything changes, and there's a real chance that it will, you will see it here first, not 3 days later buried in someone else's news update. To understand why a fault like this can go from sleepy to alarming in 5 weeks, we need to look at what has actually been happening underneath it for a very long time. 2, the sleeping fault scientists call this crack the Maacama fault. Almost nobody outside of geology has ever heard the name, and that is exactly the point. It runs northwest to southeast, cutting through the hills east of the famous San Andreas Fault, the one everybody has actually heard of. Here is a simple way to picture what is happening deep under California. 2 enormous pieces of the Earth's crust, each one bigger than a country, are sliding slowly past each other like 2 giant rough slabs of rock grinding against one another in extremely slow motion. Scientists call these 2 pieces the Pacific Plate and the North American Plate, and California happens to sit right along the line where they meet. That single fact is the entire reason California has so many earthquakes in the first place. It is not bad luck. It is simply sitting on top of the seam between 2 of the biggest moving pieces of our planet. Almost all of that sliding gets blamed on the San Andreas Fault because it is famous and it is the biggest single crack involved. But the San Andreas cannot carry all of that motion by itself. Some of it has to go somewhere else. A lot of that leftover motion travels along quieter faults further inland, and the Maacama is one of the biggest of these hidden helpers. Picture those 2 giant slabs of crust like 2 enormous rough wooden planks lying flat on the ground, pushed up against each other end to end. Now imagine someone slowly dragging one plank sideways while the other one stays put. If the surfaces were perfectly smooth, they would slide past each other easily and nothing dramatic would ever happen. But real rock is not smooth. It is rough and jagged and it catches on itself. So instead of sliding smoothly, the 2 planks get stuck together in spots, even while the force pushing them keeps building and building. Eventually, one of those stuck spots gives way all at once, and the sudden jolt of movement is what we feel as an earthquake. Every year, the 2 sides of the Maacama Fault shift past each other by about the width of a small paperclip. roughly a third of an inch. That does not sound like much, and most years, it is not much. Some of that yearly shift happens quietly, without any earthquake at all. Geologists call this creep. Imagine a rusty zipper that is slowly unsticking itself, one tiny tooth at a time, without ever fully ripping open. That is creep. You can actually see the evidence of it above ground, in places where curbs and fence lines that used to run in a perfectly straight line have slowly bent sideways over the decades, nudged just a little more each year by a fault that never even had to earthquake to move them. For a long time, people like to describe creep as a kind of safety valve, a way for a fault to let off steam quietly instead of building up to a dangerous earthquake. That idea sounds comforting, but the scientists who actually study the Maacama fault closely say it is only half true, and the missing half is the important part. Here's the problem with creep, though. It never manages to release everything. Only part of the yearly motion gets used up quietly. The rest has nowhere to go, so it just keeps building up inside the rock, like tightening a rubber band around your finger a tiny bit more every single day. You do not feel much difference from one day to the next, but stretch anything long enough, and eventually something has to give. That leftover unreleased stress is exactly what an earthquake is. It is not really the ground exploding out of nowhere. It is stored up pressure finally winning a fight it had been slowly losing for years, sometimes for centuries. Before we go further, it helps to understand just how fast that stored up energy grows once it starts getting released as bigger and bigger earthquakes. The number scientists use to measure earthquake size does not go up in a straight line. Each single number jump means the shaking released roughly 30 times more energy than the number before it. That means a magnitude 5 earthquake is not just a little stronger than a magnitude 4. It releases something like 30 times more energy. A magnitude 6 releases 30 times more energy than that, and a magnitude 7 releases 30 times more again. It is a little like comparing a single firecracker to a whole box of firecrackers going off together to an entire fireworks show. The numbers climb slowly. The actual power behind them climbs incredibly fast. And this is where the story gets a lot bigger than one small town in wine country. Scientists went looking for proof of how big this fault's past outbursts have really been. Near a small town called Willits, researchers dug down into the layers of dirt and mud that have built up over hundreds of years. Buried inside those layers, they found clear evidence that the ground had been ripped sideways, more than once, going back at least 1,200 years. To find this evidence, researchers did not just guess. They dug a long, deep trench straight across the fault line itself, cutting down through layer after layer of soil that had built up slowly over hundreds and hundreds of years, almost like the rings inside a tree trunk. Each layer represented a different slice of time. And running straight through several of those layers, in a perfectly straight line, they found the same soil pattern suddenly offset sideways, shifted a few feet away from where it should have lined up. That kind of sideways jump does not happen from wind or rain or normal erosion. It happens when the ground itself rips sideways all at once, right through the middle of an earthquake. Here's what makes that discovery so important. Small earthquakes do not usually leave a mark that lasts for centuries. The ground has to move a lot, all at once, to leave a scar that is still visible more than 1,000 years later. Scientists will not put an exact number on how strong those ancient earthquakes were, because guessing a precise size from a single measurement in the dirt would not be honest science. But when they look at how much the ground actually shifted in those old layers, their best honest guess is that some of those ancient earthquakes were far more powerful than anything this fault has produced in modern times, possibly dozens of times stronger than the earthquake that hit in June. Think about what that means. The strongest earthquake this fault has ever produced in the era of scientific record-keeping might not even be close to what this same fault has clearly done before, and could very possibly do again. So picture that stretched rubber band one more time. Creep loosens it a little every year, but it never fully lets go. It just keeps getting tighter year after year, decade after decade, sometimes century after century, until the ground finally does what the buried dirt near Willits has been quietly proving it has done before. Here's where it gets interesting, because this sleepy fault does not just sit there in isolation, minding its own business in the hills. It goes somewhere. 3. The road to the bay. Follow the Maacama fault far enough to the southeast, past vineyards and small towns, and it does not just fade out or stop. It keeps going, running in the same direction, toward one of the most crowded parts of the entire West Coast. For a long time, scientists had a real question mark about where exactly this chain of cracks led once it got closer to San Francisco Bay. They knew about 2 other faults further south, called the Rogers Creek Fault and the Hayward Fault, both known for being dangerous and both running directly underneath heavily populated cities. What nobody could prove for certain was whether these faults were actually connected underground to the same system running up through wine country, or whether they were separate cracks that just happened to line up on a map. In 2016, scientists finally got a clear answer. Using special imaging technology to see deep beneath San Pablo Bay, right where these faults disappear underwater, researchers proved that the Rogers Creek Fault and the Hayward Fault are not two separate cracks at all. They are one single continuous fault bending slightly as it crosses under the bay, stretching for a combined distance of about 120 miles. Here is why that discovery should get your attention. The Hayward Fault runs directly underneath some of the most densely packed cities in Northern California, including neighborhoods packed with homes, schools, and hospitals on the east side of the bay. More than 7 million people live in the wider San Francisco Bay Area today. That means the fault system we are talking about does not just run under a few scattered neighborhoods. It runs under a region roughly the size of some entire countries, and millions of people live and work directly on top of it every single day, most of them with no idea the ground beneath their street has a name at all. Scientists have been worried about this particular fault for a long time, and not without reason. The last time it broke in a truly major way was back in 1868, more than a century and a half ago, long before most of the buildings currently standing on top of it were ever built. Faults like this one tend to build up to a big rupture again after enough decades pass, and researchers who study it closely have spent years describing it as one of the most likely candidates in the entire country for a damaging earthquake within our lifetimes. That was true before the Cloverdale swarm ever happened. Discovering that this same fault connects underground, rock to rock, all the way up into wine country simply adds one more piece to a puzzle scientists were already paying very close attention to. Now, scientists have modeled what could happen if a very long stretch of this connected fault system broke all at once. Their most extreme scenario would be an earthquake strong enough to release around 700 times more energy than June's earthquake near Cloverdale. That is an enormous number, and it deserves an important piece of context right away. Earthquakes that rupture an entire long fault system all at once are real, but they are considerably rarer than earthquakes that break just one section at a time. The more likely scenarios scientists actually plan around involve just the Hayward Fault segment breaking on its own, which is still a genuinely serious earthquake, just not the single biggest number on the chart. Think of it a little like dominoes lined up in a very long row. It is possible, in rare cases, for one falling domino to knock down the entire line all the way to the end. But far more often, only a portion of the row actually falls before the chain reaction runs out of energy and stops. Either way, whether it is one section or the whole row, the outcome is still a real earthquake that people living nearby would absolutely feel and remember. To put that kind of earthquake in real terms, scientists who study the Hayward Fault expect that a major rupture there would be felt strongly across the entire San Francisco Bay Area at the same time, not just in one neighborhood or one city. Shaking that strong, spread across so many miles all at once, is exactly the kind of event that overwhelms hospitals, cuts off roads, and knocks out power for a huge number of people all in the same few minutes. It would not look like the small, contained event that happened near Cloverdale. It would look like an entire region dealing with the same emergency simultaneously. Let's be completely clear about one thing, because it matters. The small earthquake swarm near Cloverdale did not load extra pressure onto the Hayward Fault. There is no direct mechanical trigger connecting a small shake in wine country to a big city 100 miles away. Think of it like discovering a crack running along your ceiling, starting in your bathroom and continuing all the way into your bedroom. A leak that shows up in the bathroom does not cause a leak in the bedroom, but it does tell you something important. It tells you the entire ceiling shares the same underlying problem, and if one section is showing stress, the whole structure deserves a closer look. That is exactly the situation here. The Cloverdale sequence is happening at the northern end of a fault system that runs, uninterrupted, into the most crowded corner of Northern California. And the buried record near Willits already told us that this same system is capable of producing earthquakes far larger than anything in its modern history. None of this means the big one is coming next week. Nobody, anywhere in the world, has the ability to say that with any confidence. But it does mean that a fault most people have never heard of is directly connected, rock to rock, to one of the highest stakes earthquake risks in the entire country. To understand just how easily people can misjudge these moments, even trained scientists, we need to travel across the entire Pacific Ocean to a country that learned this lesson the hardest way possible. 4. Japan's warning from the past. 10 years ago, in April of 2016, the ground shook hard beneath Kumamoto, a city on the Japanese island of Kyushu. The earthquake measured a serious 6.2, strong enough to injure people, damage buildings, and send emergency crews rushing into action. Rescue teams worked through the night. Families whose homes seemed safe enough went back inside to gather belongings and check on damage. Everyone treated it, understandably, as the main event. 28 hours later, in the middle of the night, the same fault broke again, and this time it was much, much bigger. A magnitude 7.0 earthquake tore through the same region. collapsing buildings that had survived the first shake, trapping people who had gone back inside their homes, believing the danger had already passed, and causing far more destruction than the first earthquake had. Only after that second, larger earthquake did scientists officially relabel the first one as a foreshock, a smaller warning tremor that came before the real main event. Nobody could have known that in the moment. There was no sensor, no warning sign, no piece of scientific equipment anywhere on Earth that could have told anyone during those 28 hours that a bigger earthquake was still coming. That single case became one of the most important lessons in modern earthquake science. It proved, in the most painful way possible, that you cannot always trust your gut feeling that the worst has already happened. Here's the part that should make anyone nervous, and also the part that should keep anyone from panicking. Scientists have studied thousands of earthquakes around the world to figure out how often a smaller one is quietly followed by something bigger. The answer, it turns out, is not very often. Somewhere around 1 time in 20, a bigger earthquake follows within about a week. That means about 19 times out of 20, the earthquake you just felt really was the biggest one coming, and everything simply settles down afterward exactly the way you would hope. That is genuinely good news, and it is worth remembering any time a headline like this one starts to feel scary. But think about what that 1 time in 20 actually means in practice. It means there is no way to look at any single earthquake right when it happens, and know for certain which group it belongs to. Every single moderate earthquake anywhere on Earth is either the harmless 19 out of 20, or it is the rare 20th one that changes everything, and in the moment it happens, it looks exactly the same either way. That is the uncomfortable truth sitting underneath every single one of these stories, in Cloverdale and Kumamoto, and everywhere else on the planet where the ground has ever cracked. Which brings us to this year. In the final days of July, almost exactly 10 years after that lesson was learned, the ground shook again in the very same region of Japan. This earthquake measured a powerful 7.1, one of the strongest to hit Kumamoto in decades. In a couple of nearby towns, the shaking reached the absolute highest level Japan's earthquake intensity scale can even measure, a level so extreme that people cannot stay standing. Furniture gets thrown into the air, and concrete walls can crack apart. The destruction was serious and heartbreaking. Part of an old castle wall, already repaired once before, collapsed again. A major highway split apart in sections. Thousands of homes lost power, and fires broke out in parts of the city. At a shopping mall, part of the building came down during the shaking, and shortly afterward, an explosion believed to be caused by a gas leak tore through the structure, trapping people inside. Rescue crews worked around the clock, searching for survivors. Dozens of people lost their lives, and officials warned that the number could still climb as search efforts continued. Thousands of rescue workers and soldiers were sent into the region within hours, working through rubble and collapsed buildings, searching for anyone who might still be trapped. Hundreds of thousands of residents were moved into evacuation centers while their homes were checked for damage. It is worth remembering that this same region had already been rebuilding from that devastating 2016 earthquake for a full decade. Some of the buildings damaged this time had only just reopened a few weeks earlier, freshly repaired from the last disaster before the ground broke again. For a community that had spent an entire decade rebuilding, watching familiar streets shake apart all over again is the kind of thing that is hard to put into words. Government leaders publicly urged everyone in the hardest hit areas to stay alert and prepared for the possibility of another strong earthquake, a direct echo of the lesson learned back in 2016. Here's where it gets interesting, and it connects directly back to something we mentioned earlier. Japan has one of the most advanced earthquake warning systems on the entire planet. The moment sensors detect the very first hint of shaking, the system automatically fires off alerts to millions of phones, warning people that stronger shaking is on the way. It is an incredible piece of technology, and it has genuinely saved lives. But it has one unavoidable limit, and it comes down to simple physics rather than any kind of flaw or mistake. An earthquake has to actually begin before any machine can detect that it has begun. For people standing far away from where the ground first broke, that early alert can arrive many seconds, sometimes even close to a minute before the worst shaking reaches them. That is genuinely enough time to duck under a table, step away from a window, or brace yourself. But for people standing almost directly on top of where the earthquake started, the warning and the shaking arrive at almost the exact same moment, sometimes with the shaking arriving first. Think of it like a lifeguard blowing a warning whistle the instant a huge wave starts to form far out at sea. Someone standing way down the beach has plenty of time to hear that whistle and get out of the water. Someone standing right where the wave first rose up barely gets a warning at all because the wave and the sound of the whistle are racing toward them together. That is not a broken system. That is simply how fast the ocean, or in this case the ground, actually moves. California has its own version of this same technology, and it already proved this exact point during June's earthquake near Cloverdale. Within about 5 seconds of the ground first breaking, the system had already fired off alerts to hundreds of thousands of phones across the region. 5 seconds sounds impressively fast, and it is. But in those same 5 seconds, the shaking itself had already traveled more than 10 miles outward from where it started. Anyone standing within that 10-mile circle was already feeling the ground move before their phone ever had the chance to buzz. Farther out, in places like San Francisco, people genuinely got a real head start, sometimes 20 or 30 seconds of warning before anything reached them at all. That gap says everything you need to know about how these systems actually work. They are brilliant at protecting the people standing farther away. They were never able to protect the people standing closest to where it all begins, and they never will be, no matter how advanced the technology gets, because nothing can travel faster than the moment it is trying to warn you about. That single, simple fact reshapes how we should think about every early warning system on Earth, including the ones protecting California right now. These systems are incredible tools for detecting an earthquake and warning the people standing farther away. They were never designed, and they were never able to warn the people standing closest to where it all begins. So if Japan and California are on opposite sides of an ocean, with no earthquake actually causing the other, why does watching them side by side matter at all? To answer that, we need to zoom out much further than either country, all the way to a stretch of empty ocean where something even stranger has been happening. 5. The quiet spot. Nobody can explain. Thousands of miles from both California and Japan, near the island nation of Tonga in the South Pacific, sits one of the fastest moving cracks on the entire planet. 2 enormous slabs of the Earth's crust collide there, with one sliding beneath the other, at a pace far quicker than almost anywhere else on Earth. Because of that speed, this stretch of ocean floor produces earthquakes constantly, dozens of small to medium ones in a normal month, without ever making international news. Both this stretch of ocean near Tonga and the fault system running underneath California actually belong to the same enormous ring of cracks that wraps almost all the way around the edge of the Pacific Ocean. A ring so active that scientists nicknamed it the Ring of Fire a long time ago. On an average day, somewhere along that ring, and elsewhere around the planet, the Earth produces around 50 to 60 earthquakes strong enough to measure above magnitude 4. Most of them happen out in the ocean or in empty stretches of land, and almost nobody ever notices. It is only when a handful of them line up close together in time, the way Japan, California, and Tonga just did, that people start to notice the pattern at all, even when there is no real link connecting them. In the same roughly 48-hour window as the Kumamoto earthquake and the Cloverdale swarm, this stretch of ocean floor also lit up, producing a noticeably heavy cluster of earthquakes in the magnitude 4 and 5 range on both the northern and southern parts of the same fault line. On its own, a busy few days at Tonga is not unusual. This particular crack is simply an active place. But here is the detail that actually caught scientists' attention, and it is not the busy part at all. Right between those two noisy clusters sits a stretch of the same fault that has produced almost no earthquakes whatsoever, not in the last week, not in the last month. A quiet gap sitting between two loud active sections should, in theory, make you feel better. Instead, among people who study this for a living, it does the opposite. A silent stretch of fault can mean one of two very different things, and there is currently no reliable way to tell which one you are looking at just by watching from the outside. It might be quiet because that section is sliding smoothly and gently, releasing its pressure a little at a time without ever needing a big dramatic earthquake. That would be the reassuring explanation. Or it might be quiet because that section is locked completely still, jammed together so tightly that it cannot move at all, silently storing up pressure for some future release. That would be the far less reassuring explanation. From the outside, both possibilities look identical. Nothing happens, month after month, right up until the moment something finally does. Think of it like the lid on a stubborn jar. Sometimes, a lid that will not budge is just loose enough that it is quietly working its way free without you even noticing. Other times, that same stuck lid is jammed on so tightly that when it finally does move, it snaps loose all at once. Looking at the jar from across the room, both jars look exactly the same, closed and silent. The only way to really know the difference is to measure it directly, which is exactly what scientists try to do using extremely sensitive equipment planted right on top of these faults, tracking the ground's position down to fractions of an inch year after year, waiting to see which kind of silence they are actually looking at. If that idea sounds uncomfortably familiar, it should, because California has its own version of exactly this puzzle. The stretch of the San Andreas Fault, sitting just offshore of Northern California, has produced almost no recorded earthquakes in the modern era. Barely anything shows up there on the charts. And yet that very same quiet stretch of fault is the one responsible for the massive 1906 San Francisco earthquake, one of the most destructive earthquakes in American history. A silent fault is not automatically a safe fault. Sometimes silence is exactly what pressure sounds like right before it finally breaks. Now, let's be completely honest about one more thing, because it matters. Nothing that happened in Japan actually caused anything to happen in California, and nothing happening in the Pacific near Tonga is causing either of them. On an ordinary week, dozens of earthquakes above magnitude 4 happen somewhere on Earth without anyone noticing. When you're only looking at 3 of them side by side in the same short window of time, it can start to feel like a pattern, like a chain reaction spreading across the planet. It is not. Each of these 3 places is simply doing its own thing, on its own schedule, driven by its own buildup of pressure. What connects them is not cause and effect. What connects them is that each one, in its own way, is quietly teaching us the exact same lesson, that the ground can look calm right up until the moment it very clearly is not. So here is what actually matters most going forward, and it has nothing to do with guessing the next big number. Scientists are watching the shape of the aftershocks near Cloverdale extremely closely over the coming days. If those small shakes stay tightly clustered right around where they already are, that is the boring, expected outcome, a sequence slowly calming itself back down. But if those aftershocks begin to spread out, stretching further along the same fault line, especially toward the towns and cities further southeast, that would be the exact warning sign that stress is spreading onto new sections of ground, which is precisely the process that can turn a moderate sequence into something people remember for decades. The official forecast window for a notable follow-up earthquake near Cloverdale is still open for a few more days. Somewhere out on that quiet stretch near Tonga, scientists are watching for the exact same kind of clue, waiting to see whether that silent gap ever starts to speak up on its own. Neither answer is guaranteed, and neither one can be rushed. Earthquakes do not work on a schedule that fits neatly into a headline or a countdown clock. They work on the schedule of the rock itself, and right now, in 3 very different corners of the planet, that rock is still deciding what happens next. Before you go, stories like this one are exactly why we started making these videos in the first place. The ground under our feet is constantly moving in ways almost nobody ever talks about, and the moment you actually understand what is happening down there, ordinary news stories start to look completely different. If this kind of story genuinely fascinates you, do us a favor and hit like, subscribe, and tap that notification bell, because we are going to keep following this fault as the next few days unfold, and you will not want to miss where it goes. And if this video has you thinking about what you would actually do if a big one hit near you, grab our Earthquake Survival Guide ebook. The link is in the description and pinned at the top of the comments. Here's a question for you before you head out. If you found out today that your own city sat at the end of a hidden crack like this one, would you actually want to know about it, or would you honestly rather not? Drop your answer in the comments, and if you want to understand exactly how those earthquake warning apps on your phone work, and why they cannot always save the people standing closest to the shaking, go check out our other video on that right after this one.